Good morning. This is a live stream of the Earth 106, and I am just getting set up. So this is a moment while I'm setting up. You can just relax. We will begin in just a moment. All right. So we are live, and I'm waiting for people to join. I'm going to go ahead and set up some of the stuff that we want to cover. All right. Good morning, everybody. We are just going to go to our Canvas shell, take a look, and see for a moment what I need to tell you. Okay, Earth 106. Hey, 1 second, please. I want to see how we did on the midterm. Okay, and I have most of the people have turned in the midterm. I have a few people who have not. So a couple of things. I have 2 people who have not. So if you have not yet turned in the midterm, you want to be sure to do that. Also, if you want to send me, I think the midterm specified, I'll go ahead and put this back on. The midterm specified that for the numerical answers, I would suggest writing the work on a separate piece of paper and sending me a picture of your response. You don't have to do that, but if you want partial credit, or if your answers are wrong, you can show me your work. I can figure out what went wrong. So I have received pictures from several people, but if you have not yet sent me those pictures, go ahead and send me the pictures. That would be great. Okay, so we're going to go ahead and get started. Okay, so let's look at the student view. What do you have to do? I don't think I have anything. Oh, how about March outside activity? So we are really in trouble as far as outside activities, aren't we? We're not supposed to come in contact with anybody. So what's a good solution? A good solution is, since you're going to be at home, hey, we got 2 more people. Since you're going to be at home anyways, why don't you watch an online recorded lecture and use that as your outside activity? This way you can get the job done and you learn something interesting, and you have to stay inside anyways. So I'm going to go ahead and show you, and then I'll put a link up for you in the future. I really recommend highly some NASA lectures that are available. They're called the Carmen lecture series. Let me go ahead and take you to that website now. And so we're going to go NASA, of course, Carmen lectures. Might be von Carmen, but oh, it is von Carmen. Oh, I didn't even spell it right. Okay, good. Good thing that Google knows what I'm talking about. Von Carmen lecture series. Okay, so in 2020, I imagine some of these lectures are going to be canceled, but you can actually look at recorded lectures, and these are recorded from this year, or go down to the archive. So take a look at 2019, and there's lots and lots of lectures to look at, and actually, wow, yes, all kinds of interesting things. I'm sure you will find something interesting. And even though it's not a live lecture, you're looking at somebody speaking passionately, hopefully, and gaining something from that experience. So go ahead and write that up. Be sure to include the link to the cast, right? So if I click on this right here, you could go ahead and include this link. Copy that link for me and include that in your write-up so that I have a place to go and watch myself. Okay, if I find it interesting, I will want to go watch it too. Okay, so that's your outside activity. What about participation? I don't have, I need to put up a participation. And so after the lecture is over, after whatever material I covered today in lecture, I'm going to write a quiz for you. And your grade, your participation grade will be based on that that score. So go ahead and look for that. It'll probably take me like an hour after our lecture or so. But later this morning, you can go ahead and do that. And your score on that will be your participation. Now, I've been doing this a couple of times already, and I found that some people don't get a very high score the first time. And they're like, well, I watched the lecture. Well, did you take notes? Did you really pay attention? So what I'm going to do is, yeah, I know. Why am I doing this? Well, okay, I'm going to be nice. If you don't get the 10 points, which is what you want to score on the first try, you do get one more try, okay? The answers won't be shown until after your second try, unless you get a perfect score, you know you got it right. The questions are not meant to be super difficult, but did you get the content? Did you actually pay attention and learn something today? Okay, so in a way, I will actually make sure that you're participating. I know you are. Thank you guys for being here. And by the way, you might see that there is a little live chat window over there. If you have questions or something is unclear, please make a note and I'll look at that before, periodically. And if I find something is wrong, then I want to go ahead and try to fix it. So if you don't understand something that I'm talking about, please raise your hand or type something, a comment in the box. Okay, thank you guys for joining me. So actually, we're going to start off. You just had a lecture. Okay, I'm good at this. You just had a midterm. And on the midterm, I asked you some questions about black holes. In particular, we talked about the Schwarzschild radius, the event horizon of the black hole. And I want to let you know that the black holes that we were talking about were kind of the simplest possible black hole. And I don't mean to belittle it, but it's probably, yes, it's probably how we're going to do it. But anyways, the question was, are we usually going to do live streaming? I don't know. Actually, now I have a pro account for Zoom. So I actually can do a Zoom meeting as well. But the one thing I like about the YouTube is it records it immediately. And so anybody can come in at any point and then you can review it afterwards. So I do kind of like it, but I agree, your participation is not as good. But I am reading your comments, Julian, I got that. So if the rest of you want to comment, that's great too. So back to the question. So I told you about a black hole. We talked about black holes. We talked about different size black holes. But one thing that we didn't talk about is two other factors that might change in a black hole. So today I want to introduce you to black holes that can have a charge. They're not neutral. They have a positive or negative net charge. And the second type is a rotating black hole. Now, I have to be honest, I would bet that most black holes are rotating anyways. So we really have not discussed black holes that are going to be very realistic. You do not need to watch live. The question is, do I need to watch live to get full credit? You do not. If you would rather sleep in and watch the recording, that is fine. The benefit of watching live is you can ask questions like you just did, and I can respond. Okay, so anyways, yes. Okay, so the two types of black holes we want to discuss right now are black holes that have a net charge, either positive or negative, and then black holes that are rotating. So we're going to go to my favorite website in the world, Wikipedia, and let's talk about charged rotating black holes. Well, that's actually not what we want to talk about. We're going to talk about whether it is charged or whether it is rotating. We're going to go to Wikipedia. Okay, let's see. Charged black holes. Okay. So black holes have different things. They have mass, they can have angular momentum, they can have charge. I would write that down. Those are the three things that we can characterize a black hole with. Mass we've already dealt with, right? The mass of the black hole determines the strength of gravity. which is the size of the event horizon, you know, the short shield radius. What we haven't done is talk about the angular momentum or the electric charge. We have assumed, by the way, that these were, I didn't tell you that explicitly, but the black holes were not rotating and the net charge was 0, okay? Otherwise, what's interesting is that there will not only be a force of gravity, there will be an electric force that has to escape from the black hole somehow, right? There must be a net electric field, but with their electric field, if they're neutral, the electric field becomes 0 outside of the black hole. We can neglect it. And then the second part, I jumped out of order, is the angular momentum. Something that is rotating has angular momentum. And actually, we talked about this already several times. When things are rotating, what happens when they're rotating, if you pull the mass closer together towards the axis of rotation, what happens is it begins to rotate faster. The analogy or the useful example is the ice skater. When they're doing their spin, their arms come out, they begin to spin, and then they pull their arms together and they rotate really quickly. This is called conservation of angular momentum. So let's go ahead, and you want to write down the names just because, you know, they have names. Can you guys read this? Can somebody tell me? Can you read this? Or you can actually go to the website yourself. You can go to Wikipedia. We're on, the title is Charged Black Hole. Okay. And here are, I think there's a better place here. Hold on. You know what? Let's go ahead and let's go to the black hole one here. Black hole. Okay. Oh, well, we're going to be here soon. Okay. Okay. All right. This is, okay, this is actually what we're going to talk about today. So let's see. How about black hole? No, never mind. Okay. So actually where we were was pretty good. Let's go ahead and write it down. So here we go. Short shield black hole, no angular momentum, no electric charge. A Kerr, go ahead and write down Kerr, and that has angular momentum but no electric charge. A Reissner-Nordstrom has no angular momentum but does have an electric charge, and a Kerr-Newman has both angular momentum and electric charge. So rotating and charged black holes. Okay, so let's go ahead and just take a quick look. We're not supposed to understand everything about it. It's a little bit confusing. But the Kerr black hole, here we go. So Schwarzschild, this is the picture I was looking for actually, or sorry, the chart. So non-rotating, uncharged is a Schwarzschild. Rotating and uncharged is called Kerr. And so what should happen if it's rotating, we find out, is that the black hole will drag space-time around it. There will be an effect called frame dragging. And instead of a simple picture where we had a single event horizon, we have a new type of picture. And we're not going to get into all of the details, but you do want to sketch a picture of it if you can. Oh, lots of math. We're skipping that. We're going to look at the picture. Here we go. Okay, so let's go ahead. Woo, what's this? I don't know what that is. That is awesome. Okay, I don't know what that is. Let's go ahead and take a picture. Go ahead and sketch in your notes. This is a picture of a Kerr black hole. And so you want to notice something really important. Instead of a singularity, this is a big deal. This is a really big deal. I want you to understand an important idea that when you're rotating, you have this thing, this quantity called angular momentum. And if I were to somehow shrink all of the mass down to a point, that point can no longer have angular momentum. So a rotating black hole can never shrink down to a single point, single mathematical point. It's just not possible because then you would lose your angular momentum, and that it would violate, you know, one of our most important laws in physics, which is conservation of angular momentum. So if you notice, there's a name here. It says ring singularity. The singularity is now going to be a ring of matter. It's still compressed into a zero-dimension width, a zero length width. It's still like a point, but it's stretched into the shape of a ring. And so this ring singularity, there's another name, they call it ringularity. You should know that. A ringularity allows you to have angular momentum even though the matter has been compressed down to the smallest possible state. So you'll notice that there are actually multiple event horizons here. And that's kind of strange. Don't worry too much about that. I don't quite get it either. I mean, what does it even mean, right? Well, it has to do with escaping, right? The event horizon is escaping from the black hole. But if you're in a frame-dragged location, it is possible that you might be able to escape, I guess, in a slightly different way. Don't worry too much about that. But I do want to talk about this other word, ergosphere, in just a moment. So you have an outer ergosphere, an inner ergosphere, which is kind of encompassing the black hole, the the black hole singularity. And then you have an inner horizon, which is more like what we would consider our event horizon. But there's actually an outer horizon. There's another event horizon here. So there's two event horizons, which is kind of wild. And then these other things called ergosphere. Now, the term erg refers to energy. So another way to say this is the energy sphere. And it has something to do with the energy of the particles, actually, right? Whether they can escape or not has to do with their energy and their location, of course. So this ergosphere has something to do with energy. That's about all you really need to know. We could go ahead and look at the definitions here. So what is the ergosphere? The ergosphere, blah, blah, the purely blah, blah, blah. Oh my gosh, this is complicated. Okay, so due to the blah, 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 okay, the ergosphere, maybe I just click that. The ergosphere is a relation, this is an easier looking picture. This is the one that I've recognized. Is a region located outside a rotating black hole's outer event horizon. Its name, blah, blah, blah. It is word derived from work, which is energy, because it is possible to extract energy and mass from this region. So the ergosphere is a place that matter and particles can escape from. And so that's kind of an interesting thing. Yeah, so other than that, this is a pretty complex kind of idea. I don't think you're supposed to know too much more about that. Basically, what did we just find out? That black holes get more complicated. If you add angular momentum, you now get a second event horizon and this new thing called the ergosphere. But let's go ahead and jump back to the charged ones just to understand a little bit more. So the idea is that now not only the gravitational field, but the electric field will penetrate past the event horizon. It must exist. Okay, do we have any pictures? Because we need a picture. Oh, there's no pictures. Oh. Okay. Well, so don't worry too much. The main thing is, okay, you're just missing it. Okay, so the main thing is that outside of the region of the black hole, one of the laws of physics states that no matter how you do it, if there's a net charge, there must be an electric field coming out of that charge. The electric field is a region of influence where charges can affect other charges. So you might remember that two positive charges repel and opposite charges attract. The black hole must do the same thing. So in addition to a force of gravity, there is an extra force of the electric force that will interact with charged particles. Okay, so I don't see any pictures, so we'll skip that. Just know that it exists, right? And then the last one that we have is a Kerr-Newman. And now we have something that is rotating. So it's got to have the Kerr, it's got to have the second event horizon. Okay. Ooh, cool. This is neat. That's a new study, a new way of doing things, by the way. Actually, it's kind of after the movie Interstellar. Ooh, there we go. Because we actually are seeing what it looks like, not by real modeling, but actually by real modeling, by sending in photons or particles, we see what would happen to them in the region. We know how to model the space-time, but we don't really know what it looks like until we send the particles in. So this is a picture showing, so it's a ray trace. We're showing you what it might look like, and it is rotating towards the observer. The left side of the black hole is rotating towards the observer. So one side of the black hole is supposed to be different than the other. Can you see it? The left side of the black hole is rotating towards the observer. Oh, okay. Oh, I see a little shift. Okay, so if you look right here, there's a little squished squished. It's oblong, right? So I guess that's all I didn't know that. That's interesting. This is the first time I've seen that. So we see that the black hole is not exactly symmetrical in appearance. And so this side over here, we see it compressed. That's because it's coming towards us. And that part is going away from us. Okay, well, that's interesting. I didn't even know that. There you go. You just learned something and I just learned something. So they do look asymmetrical because of that rotation. Interesting. Wow. Cool. Okay, so our next topic for today, we're going to jump out of chapter 6, which is black holes, and jump into chapter 7. Okay. And did you know, I'm sure I told you, so you probably know, that you can go to Wikipedia and get like a rundown. But by the way, you should read the book because you're getting details in there. And I'm going to be testing you on questions that are in there. Okay, so black holes, we're talking about black holes. Chapter 7 is the laws of thermodynamics, okay? So we are going to be talking, this is a really short summary. There's so much good stuff inside there. Okay, so let's talk about, actually this summary is not very good. Let's go ahead and talk about thermodynamics. Okay, thermodynamics. Okay, so we have this field called thermodynamics. Okay, so now what is thermodynamics? If you break the word apart, thermo means heat and dynamics means movement. So it's the movement of heat. How does heat move? And the answer is that without any help, heat energy will move from a hot object towards a cold object automatically, spontaneously. It is possible to make it go in reverse, right? Actually, we're going to talk about that. I'm your teacher. I get to tell you anything I want, right? And one of the things I really want to share with you is how does heat energy flow? And so there are 3 mechanisms that you know about. One is called conduction, the other is called convection, and the third is called radiation, okay? Now, if you're out in the vacuum of space with nothing touching you, and no material for you to influence, it's just a vacuum around you, then there's only one way for heat energy to come in or out of you, and that is by radiation. So radiation ends up being the most important mechanism for stars or planets or black holes in order to communicate heat energy with the universe. There's really only radiation, okay? Because you can't touch, which is required for conduction, and you can't influence a second material, the convective fluid, and let it carry the energy for you. So there it is, it's just radiation. So we've talked a little bit about radiation before. We called it black body radiation, and it's based on the concept that everything with a temperature is going to radiate light, and this is a really beautiful thing. Now, you may not remember, but I did mention this term called emissivity. So emissivity is a concept that the quality of radiation or the ability to radiate is based on how emissive the material is. It turns out that emissivity is exactly the same as absorption ability. So, and a material that is good at absorbing light energy is also going to be good at radiating light energy. So we mentioned if something is light colored or dark colored, that lets you know its ability to absorb and emit light. So things that are light in color, very white, for example, they reflect light. They don't absorb light, which means they're not very good at emitting light either. But on the other hand, things that are very dark, really, we talked about Vanta black and then black 2.0. Things that are very dark will absorb very well. They're also going to be really excellent at radiating light. So the darkness of a material is indicative of its ability to absorb or radiate. Okay, so that's pretty much going to be it. But before we do all that, let's go ahead and jump into thermodynamics and talk about the laws of thermodynamics. So you need to know the laws of thermodynamics in order to see, this is one of Hawking's biggest contributions to the field, in order to see that black holes are thermodynamic objects and therefore follow the laws of thermodynamics. And we're going to learn how that works, okay? So anyways, so what are the laws of thermodynamics? Okay, there is a zero law, and then there's 3 more. Okay, so zero law, let's talk about the zero. There we go, zeroth law, the laws of thermodynamics. We'll jump down here. The zeroth law says that if two systems are in thermal equilibrium with a third, they are also in thermal equilibrium with each other. So those words, what does that mean, thermal equilibrium? It means that if you put them in contact with each other, no heat energy will flow. And the reason why is they have the same temperature. So the Zeroth Law basically is saying there's this concept called temperature, and it makes sense, right? It's something that we should talk about. And if two objects are the same temperature, no heat energy will flow between them. They are in thermodynamic equilibrium. If I put this one in contact with this, no heat energy flowed. And if I find something new, like my head, no heat energy flows, then I know that all three of them are at the same temperature. What a silly thing. I'm getting paid, by the way. You guys are watching me getting paid. Yeah, okay. So, Zeroth Law, there's a concept of temperature is meaningful. And how do we measure temperature in thermodynamics? Kelvin, right? So what is the coldest temperature that anything can be? Absolute zero. Okay, that is 0 Kelvin. That is the cold. There's no negative numbers in the Kelvin scale. That's important. Okay. Next up. The first law. Oh my gosh, it looks very complicated. Actually, it really does, because we haven't talked about any of this. Don't worry, you could write it down if you want. I don't know. Should you? Did you write it down? Okay. I don't know. You don't need to write it down. Let's see. Let's see if we can write something down, though. I lost it. Here we go. First law. In a process without transfer of matter, the change in internal energy is equal to the change in heat less the thermo. Oh my gosh, this is confusing. Okay, so actually, this Wikipedia version is not what I want you to write down. I want you to write down that the first law of thermodynamics is conservation of energy. Okay, that you already know about. It says energy cannot be created or destroyed, only transformed from one kind to another. That is what the first law is saying. Okay, so that's what you should know. That's a mathematical way to state it, but don't worry about that. You don't have to do that. But I will talk a little bit more about that. Okay, here we go. The second law of thermodynamics. Heat cannot spontaneously flow from a cooler location to a hotter location. Okay, that's what it says, but there's another way to discuss it that I'd like you to know about. And it has to do with the concept of entropy. Everybody write that word down, entropy. It turns out we are experiencing a very high entropic event. The chaos of coronavirus is definitely leading to a lot of disruption. But we're going to find a way to survive and get through this and be stronger for it. So remember to be kind to one another. And if you have people you get frustrated with, take a moment, take a deep breath, relax. Okay, it's going to be okay. We're going to get through this. But give everybody room for making mistakes and being human. Okay, you're human too, by the way. If you make a mistake, learn from it and move forward. Okay, don't let it get you down. All right. Entropy. Let's talk about entropy. Entropy is a measure of the disorder of a system. So I usually, if I were in the classroom, one of the things I would point out to us, because we're in the 8 a.m. class, when we walk in, the classroom is really nice and neat and orderly. And I would say that that is a low entropy state, right? When everything is organized, when everything is orderly, that's low entropy. But by the end of the day, what happens to the room? It becomes all jumbled up. The desks aren't in lines anymore. There's garbage on the floor. There's dirt, whatever. They're turned backwards. So the entropy of the system has gone up. So what we're going to do is talk about the entropy of the entire universe. This is a big deal, I know. How do we do that? Well, it's the law of thermodynamics that states that the entropy of the entire universe is a monotonic increasing function. Okay, so what does that mean? If you don't know the math word monotonic, it says that it can stay the same. That's a very special kind of situation. If the entropy doesn't change, the process is called a reversible process, because you can go back and forth and you didn't change the level of entropy. You may have changed the state of the system, but you didn't really make it more or less disorganized. Or it can go up, right? And in fact, that's the net thing that must happen to the universe. Over time, the entropy of the universe can stay the same, it's possible, or go up, and that's it. It can never go down. The entropy of the universe cannot decrease. It cannot get smaller. Now, it's really important that you think about the fact that you exist. You are kind of raging against the universe because you are a highly organized system. Your entropy is kind of low, right? There's lots of other things in the universe that are much more chaotic, but you and your brain and your memories are actually organized order, right? So life itself is against entropy, right? It somehow lowers the entropy locally, right? Because in the act of living and organizing your memories and living and existing and being more organized, you create more disorder in the rest of the universe. So unfortunately, it's the law of thermodynamics. You cannot reduce the entropy of the universe. So going back to the classroom analogy, we come into the classroom and it's all neat and organized in the morning, but it gets, chaotic and messy, higher entropy by the end of the day. Somebody comes in, they're paid, a janitor comes in to clean the room and organize it and make it all fresh and nice again. And when they did that, they just lowered the entropy of the room. But they had to expend energy. They had to move around. They had to sweat. They worked to make that happen. And in the process, their heat energy went out into the universe, causing the atoms and gas molecules to move faster and more chaotically, which increased the overall entropy of the universe. You cannot make the universe's entropy go down. It is a violation of the second law of thermodynamics. Okay, so I've gone on and on. Hopefully you understand the principle. Second law. So entropy can only go up. This is why heat spontaneously cannot flow from colder to hotter. Another example is if I take a glass and I drop it, right? What's going to happen? It's going to shatter. So it went from an organized cup to all these pieces everywhere, right? That's a higher entropy state. Is it possible that the glass will reassemble itself back into a cup? Well, you would never see that, right? Never in a human lifetime, probably never in the lifetime of the universe. And so we are going to say that entropy also says something like that things that are highly disorganized do not just spontaneously become more organized. That doesn't seem to happen. You need to do something to make it happen. And in the process, again, you create more entropy, more disorder in the rest of the universe. So local entropy can decrease, but not universal entropy. Okay, final law, the third law. The third law says, as the temperature of a system approaches absolute zero, all processes cease and the entropy approaches a minimum value, which means zero, right? It has zero entropy. Well, minimum value, okay. It may be that it's not exactly zero, but it's so close to zero that we can kind of ignore it. But basically, when things are at absolute zero, they don't move anymore. And they're frozen in a state that allows them to exist, I guess. And by the way, it's impossible. That's actually what the third law says. It is actually impossible to get to absolute zero. And you might think of it as similar to the concept of why we could never get to the speed of light. Very similar. In order to cool something down, what do you need to do? You need to remove heat energy from it. But I'm about to tell you something pretty critical. The third law says that the efficiency or the difficulty of removing heat energy goes down, the efficiency goes down the closer you get to absolute zero. And so you can try, but what happens is you become less and less efficient the closer you get to absolute zero. If you are just a tiny little bit above absolute zero, your efficiency is nearly zero. And therefore, everything you're doing has no effect. It doesn't actually accomplish anything. So the closer you get to absolute zero, the harder it is to remove the heat energy from a system. Okay, so this is an important thing. You can never get to absolute zero because the efficiency becomes so so low, right? You can basically zero efficiency when you get to absolute zero. So you need another way to think about it. Well, let's say I spontaneously cool something off, which means I need to put that system in contact with something colder. Well, how do you do that? What's colder than that? There's no such thing, right? Absolute zero is the lowest temperature you can get to. So anyways, have we ever gotten close? And actually, you need to know that the answer is yes. We have gotten incredibly close. And even though we've never gotten to absolute zero, we have gotten to within billions of absolute zero, nano-Kelvin. Okay, so we have gotten within, a billionth of a Kelvin of absolute zero. We do get very, very low, but that's it. We can't go much lower than that. And maybe in the future, but not right now. Okay, so we got the 4 laws. Zero kind of doesn't count. It just says the concept of temperature, the 3 laws. And then we're going to somehow figure out how does this apply to black holes. But before I do, let me kind of talk a little bit more about something interesting, which is thermodynamics, okay? And maybe try to explain a concept, because I want you to get this efficiency idea. I'm going to go ahead and move our board over. Actually, I could have just moved. Oh, you know what? I think I should just do that. Let me just do that. I changed my mind. This is new. Everything's new, right? It's all good. Everything's going to be fine. Every little thing is going to be all right. Don't worry. Okay, I know what I'm going to do. I'm going to shut off the screen. And then I'm going to bring our whiteboard over. And that way, this way I can push it in and out of place. Oh, isn't this lovely? And it looks crooked. So how do I fix that? Okay, there we go. All right. Ooh, look at all the lights out there. Okay, so what we're going to do is we're going to write down some ideas related to thermodynamics, related to energy, related to efficiency. And this is not strictly required. Well, yeah, actually it is. Never mind. I'm your teacher. You got to know this. Okay. So I want to talk to you about the concept of heat flow, right? Heat flow. Okay, heat flow. Can you read that? Can somebody tell me? Can you read that? Can you read that? Heat flow. Okay, I'm hoping you can read that. We're going to call that Q. Q is heat flow. So Q, actually heat energy flow. Okay, heat Q. So the way it works, let's see if I can turn off that other light. Can you guys still see? Okay, nobody's talking. Okay, can you guys still see? Heat flow Q. Okay, so I'm hoping it works. So the idea is, in order for heat energy to flow, I need a hot body and I need a cold body. Okay, and which direction is the heat going to flow? Well, thermodynamics says spontaneously the heat will flow from hot to cold. You don't need to do anything, right? It's just going to do that. The universe has said that's the rules. Thermodynamics allows this to happen. So heat energy flows from hot to cold without any help. Now, is it possible to make it go the wrong way? And the answer is sure, you can do that. But there are some rules, right? There's some rules for that. So I want to show you guys an idea that's kind of important. And this is the concept of an engine, right? The concept of a thermodynamic engine. So what we're going to do is we're going to put in an engine. This is like a car engine or anything that does something useful with heat energy. So a car is very, very much like this. How do you make this engine do something, right? This is an engine. So make sure you're drawing the diagram that I have right here. I have the hot side, I have the cold side, and I have an engine. So an internal combustion engine is an excellent example. The way it works is you burn fuel inside of the car engine, which makes something really hot. And that actually creates something called pressure, which pushes on the pistons. But that will be trying to get out, right? It tries to get out to the outside world, which is the cold side. And the way it works is the engine is going to capture some of that energy. So would you follow along with me as I describe specifically what happens? So this is called the hot reservoir. And this is just language. There's some words, reservoir. Oh man, I don't know how to spell reservoir. Hold on. Let's look it up. Reservoir. Okay, it is reservoir. Reservoir. Okay, good. So a hot reservoir, and down here we'll have a cold reservoir. And what does that mean? A cold or a hot reservoir is something that can give or receive heat energy and not change temperature. Can you guys still read this? Oh, a little bit of glare from my screen. Huh. Okay, well, all right, you're listening to me, right? Then you can write it down. Okay, so here's the idea that heat energy is going to come out of the hot reservoir. Let's draw an arrow. And this is the flow of heat energy into my engine. And I'm going to give it a name. I'm going to call it QH, the heat energy coming out of the hot side of my thermodynamic process. And it turns out that you can, one of the laws, the third law says you can never use all the energy up. Okay. Now the car engine is going to do something. It's going to take me around, right? It's going to, and by the way, electrical engines work in a different way, but it's based on the same laws of thermodynamics. It's just a little bit more difficult to talk about it because it's not strictly a thermal process, but there's something related in electricity and magnetism that you can use. Okay, so your electric vehicles work in the same. They can't violate the laws of thermodynamics. Okay, so the engine is going to do something. It's going to carry you around town. And we call that work, right? That's called work. So the energy that you get out of a car engine is the work energy. But you cannot actually use all of this energy. So no matter what, you might have noticed that you have an exhaust pipe, right? That's just wasted energy that goes into the atmosphere, okay? And that waste energy is going to be a certain amount of heat energy. We'll call that QC. Okay, so what I want to do is showing you how to use the laws of thermodynamics. I want to teach you something important. A heat engine, right, is something that's using the heat energy to accomplish something useful. But it must follow the laws of thermodynamics, in particular, the first law. So how do we apply the first law to this system? And the answer is, well, if you put in QH, right? Part of that energy can come out as work, but the rest of it is wasted and is expelled to the universe, right? Expelled to the atmosphere is called QC. So in fact, what did I just use? This is conservation of energy. That's it, just conservation of energy. So the heat energy that I put in and the work that I got out, plus the wasted heat energy, have to balance, right? I can't get any free energy. So what do we mean by efficiency? Okay, so you need to know the word efficiency. What is the efficiency of the system? And efficiency can be different. If you were in engineering class, you're going to learn there's more than one way to talk about efficiency, but we're going to just use the simplest efficiency we can, and I'll call it efficiency. It's going to be, it's a percent, right, or a fraction less than 1. And what it is the it's the work that you get out divided by the heat energy that you put in. So that's our efficiency right there. And, you know, that's what it is. So it can never be 100%. That's another way to state the third law of thermodynamics, that you can never get to absolute zero. You can actually never use up all of the energy in a thermodynamic engine. So, okay, great. Okay, so let's see. I do want to tell you that somebody a long time ago came up with what they considered to be the optimal, the best thermodynamic engine. And I'm going to write his name down for you. So it turns out that there is a theoretical best case scenario, right? The very, very best that you can do. So what is the best, right? This is the best efficiency. And this is actually something that engineers always start off by asking. If you're building something and you want to know what's the best I can do, it turns out the laws of thermodynamics tell you. And it's based on the temperatures of your system. How cold is your output temperature and how hot is your input temperature? Those temperatures determine the maximum efficiency that you can have. So the best efficiency is called the Carnot, C-A-R-N-O-T cycle, right? This is the Carnot cycle efficiency. And so I'm going to show you an equation that you can use now, and you should try to understand, is based on the mathematics behind the laws of thermodynamics, and it gives you the very best efficiency that you can have. Okay, so what is the Carnot efficiency? It is, hold on, let me think for a second. We want it to be, I could just look it up. It is 1 minus T if they're equal, no efficiency, 0. I want to say 1 minus T cold over T hot. No, that would be bad. Okay, it's T hot, let's see, T hot minus T cold over T hot, right? Oh, it is 1 minus. Okay, let me just make sure. Sorry about that. I don't want to tell you the wrong answer. Okay, the Carnot efficiency is, oh, okay, that is it. Okay, so T hot minus T cold over T hot, that's what it is, okay? So you can reduce it, it's 1 minus T cold over T hot. So let's try to look at how this works. If you could use absolute 0 as one of your temperatures, then you could have a theoretical efficiency of 100%. But what happens the moment something that is absolute 0 gains a little bit of heat energy? It heats up, right? So the problem with a reservoir is it has to maintain that temperature even when you put in a little bit of energy or take out a little bit of energy. And it turns out to be really incredibly difficult to do that. So now let's take a look right here. What happens as the temperatures are very close together, right? Remember, you have to use something colder. Well, I'm doing it the wrong way. Okay, hang on. I'll talk about that other one in a second. But the efficiency, this is the best efficiency you can do. If the temperatures are the same, this ratio is 1 and your efficiency becomes 0. There's no heat flow. Your efficiency is 0. So the closer you get to the temperature of the system, if your hot temperature and cold temperature are too close together, you just can't get anything out. And so one of the ideas is that when you waste your energy, this happens in a nuclear power plant as well. There's a lot of good energy in the hot core of the reactor, but then they expel all this hot water into the ocean. Why can't you use that energy? And the answer is because it's too close to the temperature of the environment, and as a result, the efficiency goes down. So you can't extract energy from that system as a result. Okay, so the Carnot efficiency. All right, so let's say that we want to go the other direction. Is it possible to make a cold system colder and a hot system hotter? Is that possible? And the answer is yes. We do it all the time. It's called an air conditioner or a refrigerator. But you have to kind of think in a little bit different way. And we call this, instead of a heat engine, we call it a heat pump. And so what it's doing is changing the location of the heat energy. And it's nothing wrong. It doesn't violate anything, but you do have to think about how that works. So we're gonna make something. We're gonna make an air conditioner right now. How do you make an air conditioner? Well, the heat energy is gonna flow in a different direction, right? We're gonna still have the cold, T cold, and we're gonna still have T hot. But this is the idea, right? You're gonna go ahead and take heat energy out of the cold system and put it into a warmer system. Okay, it doesn't want to go that way. We're going to force it. So how do you do that? Well, you need to put in energy. Okay, so in order to make this happen, it doesn't happen spontaneously. You have to actually put in energy in the form of work. Now, this could be electrical energy. You're running your air conditioner or your refrigerator, but somewhere you've got to put in the energy. When you put in the energy, what will happen? Well, a certain amount of heat will flow out of the cold system. We'll call that QC again, right? The heat energy in this time is flowing out of the cold system. We've pulled this much energy out. And what happens is that we will then have to get rid of that energy, and we'll put it up here. We'll call that Q hot, okay? So how much energy goes in and how much energy goes out? Well, the answer is conservation of energy. You cannot get more energy out of the system. I'm sorry, that's wrong. You can pull this much energy out, but actually you also did this much work. So going into this circle, which is our air conditioner, our refrigerator, you're going to write the equation like this. From the first law, we're using conservation of energy. The heat energy you pulled out, plus the work that you did to make that happen, is how much heat energy you have to get rid of. So one of the questions that people often ask is, why don't I take a refrigerator, why don't I take an air conditioner and just plunk it in the middle of a room, right? Why wouldn't it work? Why doesn't it work? And the answer is why? Because it does suck energy out of the environment and then goes around and dumps that same energy plus more energy into the environment. What would happen if you took a sealed room and put an air conditioner inside of it? And the answer is, if it was running, the room would get hotter. In order to work, what you have to do is dump the heat energy outside where it's not going to bother you. So you heat up the rest of the universe by cooling off part of the universe, right? Locally, we reduce the temperature, which, by the way, reduces the entropy, but at a cost of increasing entropy somewhere else. So again, the laws of thermodynamics require that the overall entropy of the universe must go up, right? Or could stay the same, but it must go up otherwise. Okay, so I think I got the basic idea. So we talked about how you can't lead to a less disordered system. This is how the basic thermal engines work. Let's talk about that radiation stuff. Yes, let's talk about that. So how does radiation work? It's a similar kind of idea, except what's going to happen is we have the Stefan Boltzmann equation. And so I want to talk about that, the Stefan Boltzmann equation. The Stefan Boltzmann equation is right here. This is for radiation. Radiation, we're going to do the Stefan Boltzmann equation, Stefan Boltzmann. And the equation goes like this. The luminosity of something, the amount of light per second, the luminosity, is equal to, and it's got a bunch of letters in there. So one is the emissivity. I'm going to put that first. This is called the emissivity. Okay, times this factor sigma, which is the Stefan Boltzmann constant. And again, you don't need to know that, but it's 5.67 times 10 to the minus 8. I'll give you the units in just a moment. I have to remember them. The third factor is capital A. This is the surface area. Okay. And the last factor is capital T to the fourth power. Capital T is the temperature in Kelvin, right? So I could have written that. Actually, let me go ahead and write down for you the units, right? So what are the units? So E has no units. E is just a number. If you remember, it's a number between 0 and 1, right? And 1 would be a perfect emitter, perfect absorber. 0 is a perfect reflector, I guess, right? It doesn't emit at all. What are the units of A? Well, area is measured length times width. What's the units of length times width? You would get meters times meters, meters squared. And what is the unit of temperature? It is Kelvin. And so the units for sigma, you don't need this, by the way, are going to be watts per meter squared Kelvin to the fourth. Okay, so this is something important. Watts are a unit of power. This is energy per second. So the energy per second coming out of a hot object is based on all of these factors. Do we have to do equations with this? No, you don't have to do that. But I do want to talk a little bit about how that works. Suppose you have a hot object, right? a hot object. And we said what happens? All hot objects, including you, right, are radiating light, and the type of light that they radiate changes. It can be visible or invisible light. It's not really relevant. The point is that they radiate light energy, okay? They have a radiation away from the object, right? One thing I didn't tell you, though, okay, is that because they are sitting in an environment, there's going to be a temperature of the environment as well. We could maybe say, I don't know, maybe the environment is TC, right? The cold temperature, right? It's hot, so it's radiating. Like, actually, in fact, what happens if you take something cold and put it in a hot room, right? What happens? Well, it heats up. So I have a temperature here for the original object, and I have a temperature for the room that it's in, right? And I want to think a little bit about how that works. So one thing that you want to understand is this getting hotter or cooler? And the answer is it's getting cooler, because the environment is cooler than it. What happens? It has a net loss of energy. But it's kind of important that you understand there's really two sides to this. What's happening? What's happening to the object? So I don't want to get too bogged down with the math, but I'm going to write it down just because it looks kind of cool. Let's put delta, which is the change in the internal energy. That's not quite right either. Divided by T. Okay, sorry about that. Delta U over delta T. There's not much I can do about that. It's going to be important, right? That there's energy going away, but it turns out, remember that this emissivity is also absorption ability. So it also is gaining energy from the environment. So what's going to happen over time? It's gonna go ahead and actually, I'm going to write it down specifically. What's going to happen? It's going to gain energy because of the environment. So you're going to gain energy. It's going to be positive according to this. Right? You're going to gain energy according to the environment temperature. You're going to be absorbing energy at this rate, right? Energy per second. But you're going to be losing energy because you're radiating away. So E sigma A T hot to the fourth. We're not going to do all the math, but take a look at that equation, right? What would happen if this thing, so what's the net thing? If TC is lower than TH, then what is this going to be? It's going to be negative, which means what? You're losing energy over time. You're radiating the energy away. You're cooling off, right? But what will happen eventually is you will match the temperature of your environment. We call that thermodynamic equilibrium. And then what? Well, then what does this become? And the answer is, if these temperatures are the same, the answer is 0. It doesn't change anymore. So in order to cool off, the environment must be cooler than you, right? And so that's easy, right? So actually, when you talk about you and the universe, actually, oh, maybe I should tell you. Am I jumping to that already? I'm jumping to that. I should tell you something. You guys already know this, but when we talk about black holes, right, we're talking about they're in space, right? Does space have a temperature? Well, you might know that it actually does. And does anybody listening live right now know the temperature of the universe approximately? Correct right now. Just for now, because it's going to get smaller as we go on, right? What's the current temperature of the universe? And as the universe expands, we expect this temperature to go down. We actually have made predictions of that. But what is the current temperature of the universe? That's correct. Very good. The current temperature of the universe, space, the final frontier, space, right? The vacuum of space. The temperature is about, I'll put a little squiggle, 3 Kelvin. Okay. So how does it work, right? If anything is hotter than 3 Kelvin, then you can tell me right now, is it heating up or cooling off? And of course, the answer is If it's hotter than 3 Kelvin, it must be cooling off. If you put it out in space and anything, here you got something with a temperature. If the temperature is, and so the environment is 3 Kelvin, right? If the temperature is greater than 3 Kelvin, then what does that mean? That it's going to radiate more energy than the universe is going to give it. And therefore, what? It's cooling off. Right now, it's cooling off. Now. Right? But we were about to find out that black holes are going to be very cold, right? So what if the temperature, I did this backwards. What if the temperature, I'll call it green here. What if the temperature is less than 3 Kelvin? Oh, that looks ugly. What if the temperature is less than 3 Kelvin? What happens then? If the temperature is less than 3 Kelvin, then what happens is that your environment is actually hot and you are cold, right? The environment is so what if this was 2 or 1, right? Now the environment is actually going to be giving you more energy than you are radiating. And so what's going to happen? You're going to heat up. Now, right? Right now you're heating up. Okay, so well, this is kind of an important idea. So when you talk about black holes, we're going to talk about whether or not they can evaporate, whether or not they can cool off, and the answer is can they? And the answer is, well, what's their temperature? Is it above 3 Kelvin or below 3 Kelvin? And so we will find that out. We're going to actually be able to talk about that. So they are, if they're under 3 Kelvin though, then they are heating up now. Right? And will they ever be able to cool off? Well, actually, the environment of the universe, as it expands, is supposed to get colder and colder and colder. One day, it will be very small. In fact, incredibly close to absolute zero. Maybe not absolute zero, but getting closer and closer and closer every single time. Okay, so we have discussed some of the laws of thermodynamics and a couple of the big ideas. Let's try to figure out, how did Stephen Hawking come up with a mechanism or a system that makes black holes thermodynamic? Okay, so let's put your screen back up, and I'm going to look specifically at the Wikipedia page on black hole thermodynamics. Let's see if I can find that. Okay, scrolling back up. Okay, so what do we need to start off with? Black hole thermodynamics. Now, this is actually a fun story to tell, because Stephen Hawking did not know for sure when he started working with black holes if they would in fact follow the laws of thermodynamics. We hope they did, because we really like it. We like the laws of thermodynamics, but we really didn't know for sure. And then he had some incredible insight. He started thinking about the black holes perhaps evaporating one day, and it led to some ideas that we now really believe are correct. But what you need to do is make a connection between the 4 laws of thermodynamics that we discussed and black holes. What is the equivalent when you talk about black holes? So if we start off, what was the Zeroth Law? Well, if you remember, the Zeroth Law said there's this thing called temperature, and it's a meaningful way to describe an object, right? A thermodynamic object. Well, what about black holes? What is the equivalent quantity that we want to talk about? And you might say, well, what about temperature? But it turns out that black holes are not very ordinary, and it's not very useful to just, say temperature is what we want to talk about. There's going to be a quantity which happens to be directly connected to the temperature of the black hole. And it's much easier for us to get a handle on. So what is the equivalent for black holes to the temperature? And I guess I'm just going to tell you. I'm going to just tell you. Okay, I'm going to just tell you. I'm about to just tell you. Does anybody know? Anybody want to try to type it in already? What is the equivalent to temperature for a black hole? right? So instead of describing the black hole's temperature, we're going to describe this. But we mean, basically, this is the thermodynamic equivalent of temperature. And the answer is, nobody said anything. Okay, so I'm just going to go ahead and tell you, I'm telling you, the answer is the surface gravity of the black hole plays the role of temperature. Surface gravity of a black hole plays the role of temperature. So surface gravity is our temperature. Here we go. So here we go, the zeroth law. The surface gravity, kappa. So, okay, here we go. The horizon of a constant surface gravity, the horizon has a constant surface gravity for a black hole. So this is the equivalent of the temperature. Okay, so black hole, temperature, we mean surface gravity. Okay, what about the second one? Well, it's really the same, it turns out. In fact, I'm going to go ahead and say to you, it is still the same thing. What is the first law? It's conservation of energy, and guess what? It's still conservation of energy. There's some different pieces in there, but that is what it is a statement of. It is conservation. So that one didn't change, thankfully. Okay, didn't change. Okay, here we go. The second law of thermodynamics, you might remember, is a concept of entropy, right? The entropy of the universe cannot go down. And what we're going to talk about next is what about black holes? So if you take two objects and you combine them somehow, you manipulate them. One of the objects lowers its entropy. The other one must raise its entropy so that the overall entropy either stays the same or goes up, right? That's the only thing allowed. What's an equivalent idea for two black holes? What if you take two black holes and you put them together? What happens? Well, we actually have seen this happen now. And when I say seen, I mean we've detected the gravitational waves of merging black holes. It's pretty exciting that we live in a time like this where I can tell you that. But what happens when two black holes merge is they form a larger black hole, a larger mass black hole. But they also create ripples of space-time called gravitational wave. And those are a form of energy. So conservation of energy states that the mass of the remaining black hole should not be exactly the masses of the two black holes added together. You lose some of the mass because of the radiation of gravitational waves, right? That's energy. Mass and energy are just, two kinds of energy. So what about black holes? What is the quantity which is the equivalent of entropy in a black hole? And the answer is, I feel like I wanted to tell you more about this, but I'm just going to go ahead and tell you. It is the letter A. And the letter A has appeared today already. What does the letter A represent? And the answer is the surface area of the black hole. Remember, as much as you might want to think of black holes as being two-dimensional, they are not. They are three-dimensional spheres with a Schwarzschild radius, right? In the simplest case. We're probably just going to stick to the simpler case most of the time. Just be aware of the more complicated versions and what changes, right? For example, the ringularity, which must be there because of conservation of angular momentum. So the surface area. So what are we going to say? This is the statement, right? I take two black holes and I merge them. What must be true, right? That the surface area of the new black hole must be either equal or greater than the sum of the surface areas of the original black holes. That is the statement of the second law of thermodynamics. Okay, everybody good? Okay. And finally, we have the third law of thermodynamics for black holes. So, blah, blah, blah. Okay. The third law, it is not possible for a black hole to be so large that its surface gravity is zero. It is just not possible. You can never have a kappa of zero. Remember, kappa was the surface gravity, we wrote that down. You can never have a kappa of 0. It's equivalent to saying you can never reach absolute 0 temperature. You can never have a kappa of 0, no matter what you do. Okay? So we have just stated the 4 laws of thermodynamics for black holes. You should know which one goes with which. And then we're going to try to, see if we can play with this a little bit. Actually, I don't know that we can do too much because these are pretty complicated things, but maybe that one with entropy is something that we could talk about. So let me go ahead and show you one of the ways that you could use this, and probably the only way that's really going to be relevant. By the way, we do want to talk about the temperature of a black hole as well, right? What is that temperature actually equal to? Maybe I should do that first. Would you guys like to see that? Anybody want to give me input? I only have 10 minutes left. I can't do everything today. But whatever I don't finish today, I will finish after our break. By the way, we have no classes next week. I may be in Hawaii. We'll see. I don't know. I want to go, but anyways, if it doesn't matter, we don't have class. I'll be on vacation. You'll be on vacation. I hope you'll relax. This crazy, chaotic situation, you need time to relax and connect with people if you can. Connect without going to see them. Hey, call them on the phone. All right, nobody's going to give me input. Okay, the choices were, I want to learn about temperature of a black hole, or I want to see how to apply the second law of thermodynamics, the entropy, in this case, surface area. Nobody, and no input. Okay, well, I'll just do the temperature then. We'll do the temperature. Okay. So take a look right here. This is an equation. Actually, I'm going to give you some numbers in just a minute. But this right here, the Hawking temperature, which is going to be coming up later, is kappa divided by 2 pi. So you see, it's in fact actually really close to the, oh, you wanted entropy. Okay. The temperature is in fact really closely connected to the surface gravity. And actually, by the way, just so you can see this entropy is associated with the surface area, and by a factor of 4. It's perfect, right? You can write that down too. So the way we talk about entropy is we talk about surface area, and you can see that it's basically the same concept, just multiplied by 4. Okay, so in a moment, we will learn how that works. Okay, but I actually am going to give you an actual temperature. Okay, and then maybe we can talk a little bit about how that works. Okay, so black holes emit thermal radiation. Okay, never mind. Let's see, black hole temperature. I need black hole temperature. Black hole temperature. Okay, let's see, black hole temperature. Black hole temperature. All right, black hole temperature. Okay, we're going to talk about this in just a moment. I just want to see if I can find a temperature. Oh, here we go. Okay, here we go. Cool. All right, here we go. You write this down, please. This is your equation. So if you want to calculate the temperature of a black hole, this is it. Oh, this is a big equation. Okay, all right, they've simplified it for you. Way over here, it's this number times the mass of the sun divided by the mass of the black hole. Okay, so I'm going to go ahead and write that down and show you how to use that for some simple examples. But it's pretty easy. I hope you can see. Pretty easy to do. Okay, so let's go ahead and I'm going to write that down and show you a couple of calculations, just so we can have an idea. How hot or cold are the black hole? And the answer is they are incredibly cold. Okay, so the equation you're going to use on the final exam, I guess, that's when you'll see it. The temperature of a black hole is 6.169 times 10 to the minus 8 Kelvin times this ratio, the mass of the sun divided by the mass of the black hole. Okay, so I'm going to roll this into space so we can see it. Okay. Okay, you want to write that down in your notes, and now we're going to use it a couple of times just to see how does it work. Okay, so what's a typical black hole? We said that a typical black hole has got to be more massive than our sun. In fact, what would be a typical black hole? Actually, I think, let me just throw in a couple. Let's say it's got 100 solar masses, just for a nice simple problem, right? If a nice simple problem, 100 solar masses, what happens when I put this in here? The solar mass cancels, and I get 1 divided by 100. So what is the temperature of the black hole? The temperature of the black hole is going to be 6.169 times 10 to the minus 8 Kelvin times 1 divided by 100, right? I just said we cancel that. And so you just divide this number by 100. Well, that's pretty easy to do because you just put 10 to the minus 2, right? So this is 10 to the minus 2. 1 over 100 is 10 to the minus 2. So 10 to the minus 2 times 10 to the minus 8 is 10 to the minus 10. So 6.169 times 10 to the minus 10th Kelvin. Okay, well, maybe you don't know those numbers or don't recognize that. But what's the order of magnitude? The order of magnitude is 10 to the minus 9 Kelvin. And another way to say that is a nanokelvin. A nanokelvin. Now, you might have heard me say that we have actually reached this temperature before. We have even gone a little bit below that. I just remembered another experiment I read where we've gone to the next order of magnitude. We've gone even a couple order of magnitude lower than that. We've gone to picokelvin, but like tens of picokelvin. So about 10 to the minus 11, I think, is our limit right now of human. But this is a 100 solar mass black hole. What if this black hole is much larger, right? Let's say it's a supermassive black hole. What if the mass of the black hole, let's do the one in the Milky Way, right? The mass of the black hole is 4 times 10 to the 6th solar masses. 4 times 10 to the 6th solar masses. So what is the temperature of the Milky Way black hole, right? This is our Milky Way black hole. Then you're going to get the black hole temperature is going to be 6.169, 10 to the minus 8, right? Times 1 divided by 4 times 10 to the 6th solar masses, okay? Solar mass cancels, and I have to just do this division. 6.169 divided by 4 is about 1.54 times 10 to the minus 14th Kelvin. So what do you notice? I mean, without doing any calculations, right? Just look at what happens. The larger the mass of the black hole, the colder it will be. But we said in the fourth law, we can never get to 0. No matter what we do, you will never get to 0. Okay, so I think I'm pretty much going to be done. Well, I could do one more. Do I do any more? I think it's pretty much a good place to stop. So we've seen that let's do one more. Let me just do it. What happens if you are dealing with a very small mass black hole? Oh, that's kind of a fun idea. Let's go ahead and I'm going to do a small mass black hole. So let's do a mass of a black hole that's the size of a mountain. Okay, let's make it, 10 to the 15th kilograms. Remember the mass of our sun is 1.99, about 2 times 10 to the 30th. Okay, So let's go ahead and do this calculation. What is the temperature of this? This is a primordial black hole. The temperature of the black hole will be 6.169 times 10 to the minus 8. But this time I have 1.99 times 10 to the 30th divided by, can you guys read this still? Oh man, this is working. Divided by 10 to the 15th. Okay, kilograms cancel. And I get 2 times 6 is like 1.2 times 10 to the minus 8, 10 to the positive 15th, 10 to the positive 16th, times 10 to the 8th Kelvin. I want you to notice something. That is almost a billion. It's 120 million Kelvin. Okay, so would you be able to see that black hole with your human eyes? And the answer is it would be incredibly bright. Yes, okay. So that's why we're curious to see if these things really exist, because not only will they be interesting, but we'll be able to see the light that comes out of them. Okay, so now I am finished. Thank you very much for your attention. Remember that in order to get the participation points, I will be publishing a little quiz that's based on the material of today. So everything we learned today, there'll be a little quiz. If you didn't watch from the beginning, make sure that you do watch the entire thing before you take the quiz. I'll give you 2 tries just to get a perfect score. And thank you so much and have a wonderful break. You should be reading chapter 7. Or have finished chapter 7. And if you want to go ahead and finish the book over the break, that would be awesome. Otherwise, I will be just continuing, 1 chapter at a time. But you want to finish chapter 7. Okay, so thank you so much and have a wonderful day. Bye.